Hi everyone. So now we're going to go on to Thomson 11.4, which is going to tell us about the chiral nature, chiral structure of the weak interaction. So this is going to bring home why the weak interaction actually violates parity. Okay. So the V minus A, remember V is the vector and then A is the axial vector. So V minus A is the vector, axial vector. So that's why people say V minus A. Structure of the weak interaction shows us that the vertex factor, whenever we have, let's say an electron coming in, right? And then if we have a W boson instead, which will change this to an electron neutrino, okay? This vertex factor has to be changed to, instead of this just gamma mu, it has to get changed to 1 minus gamma 5 times gamma mu, right? So this whole thing gets factored in there. Okay, and this is going to remind us, right, 1 minus gamma 5, maybe, hopefully we'll minus of this thing called the left projection operator, okay, in chapter 6, okay? This is when we were dealing with chirality, whether or not a left-handed spinner will couple with a right-handed spinner, and then these coupling can occur through these projection operators where you will project out a particular helicity of a state, okay? And the fact that the weak interaction actually violates, has the maximal the maximum amount of V minus A structure, meaning basically you have a 1 in front of both the vector part and the axial vector part with a minus sign between them, okay? What this does is that it basically, whenever you have the weak interaction, it literally projects out only the left-handed particle, okay? And we're going to talk about antiparticles in a little bit because that's going to have like a sign flip everywhere, okay? So when we're dealing with the weak interaction, you're only going to project out the left chiral part of a spinner, okay? Okay, so let's say if you started off with a right chiral spinner, okay? When you do this projection operator to it, what's going to happen is that it just makes that current completely zero, okay? But if you started off with a left chiral particle spinner, then it'll give you the left chiral part. So basically, it'll just takes out anything that's right chiral, okay? In the antiparticle case, okay, remember antiparticle behaves opposite as everybody else, okay? The weak interaction actually only interacts with the right chiral antiparticles, okay? So I'm just going to write this out, okay? With particles, right, plus the weak force, you're only going to get left-handed. But if you have an antiparticle, okay, if you want to interact with the weak force, okay, you will only get the right chiral stuff, okay? So just remember one of them, and always remember that whenever you go from particle to antiparticle, there's always a sign flip. Okay, so in the relativistic limit, where the energy of the particle is much higher than the mass of the particle, remember that chirality and helicity basically becomes the same thing, okay, in the high energy limit. So what happened is that when you have left-handed helicity particles, okay, right, if it undergoes a weak interaction, meaning it spits out a W instead of a photon, okay, so if this is the particle part, right, yeah, let's draw this, right, these are the particle version, right, you have an electron, you have an electron coming in and a neutrino coming out. Both of those are regular particles, they're not antiparticles, okay? Their helicity is going to be left-handed, okay? Remember, when they're left-handed, their momentum and their helicities are in the opposite direction, so this is going to be, they're both left-handed, okay? For antiparticles, okay, right, where you have the momentum going backward, that's how I can tell it's an antiparticle, and also the bar in the positron sign, right? Both of these are going to be right-handed. Okay. Similarly, if you have an annihilation process where you have an electron coming in and then a anti-electron coming in, right? But then the particle arrows goes this way because this is an anti-particle. Okay. The electron is going to be left-handed. Okay. Okay. And then the anti-neutrino is going to be right-handed. Okay. Right. And similarly, you have this is the anti-particle, which will be right-handed. This is the particle where it'll be left-handed. Okay. All right. So how does that affect things when we're doing interaction? Okay. So this is the reason why the weak interaction actually violates parity. Why is that? Okay. So now we're going to look at these parity diagram. So let's look at just maybe like I think we're looking at this diagram here, right? Let's just highlight this one. Okay. Okay. Where we're basically colliding an electron with an anti-neutrino, right? So you have an anti-neutrino coming from the left, you have an electron coming to the right. Okay. Their momentum is going towards each other. Okay. Right. So that means the anti-neutrino has to be right-handed, therefore the helicity has to be drawn to the right. The particle has to be left-handed, so therefore its momentum and its helicity has to be drawn in opposite direction. So therefore that's why this arrow is also pointed to the right. All right, let's see what happens when we do a parity transformation. By parity, I mean I'm going to flip all the coordinates, all the spatial coordinates. So negative x becomes positive x, z becomes negative z, and stuff like that, right? Since this is let's say this is in the z direction, right? When we do a parity transformation, basically instead of the neutrino going from left to right, the neutrino now goes from right. Instead of the neutrino going from left to right, the neutrinos actually go from right to left. So therefore, right, the momentum switch direction. Okay. Similarly, right, the momentum of the electron also flipped direction. But helicity is an axial vector. So let's see, v minus a. So this is s dot p. Okay. Right. So this is positive, and this is negative, right? Sorry. Yeah, so helicity is actually a pseudoscalar, okay? Where, right, when you flip the directions of using this parity violation, the helicity does not change. It stays the same, right? Now we have a right-handed particle, which is not allowed, right, under the weak interaction. They don't couple to the weak force. And then a left-handed antiparticle, which also does not couple to the weak force. And therefore, this scattering this interaction never can happen. So the amplitude for this is actually equal to 0. Okay. So this is the interesting thing about the weak interaction, where if you were to do the same interactions in the mirror universe or the parity transform universe, right, some interactions that were possible becomes impossible. Okay. So that's it for this section, and then I will stop.